And I would like to invite a last speaker, actually, of today, which will be Marcel Štolc from Astronomical Institute in Prague. And he'll be speaking about gappy, from gappy to disks, to ring signatures of the accretion disks, radial structures in profiles of the reflections line. So if, yes, we can see the talk.
Perfect. Yeah. So thank you for having me and the opportunity to speak at this workshop. I would like to say a couple of words about a project of ours that's about the theoretical study of spectral line profiles of radiation coming from the inner parts of the galactic core. So first, I would like to introduce and remind the unified model of an active galactic nucleus, or AGN for short, which points out to the existence of supermassive black hole at its center, which is supposed to be surrounded by an accretion disk. Then there are the regions called broad line region and narrow line region, which are both responsible for producing the broad optical lines and narrow optical lines, so respectively, so hence their names. And in some cases, there might also be present a dusty component surrounding the galactic core in form of an obscuring torus, which is most noticeable in an AGN view. And then as the last component in this simple model is the high energetic relativistic ionized matter flow in form of jet, which flows across the rotational axis of the system. So we follow up with the work from Schubert and Karas from 1999 and Karas and Schubert from 2001, which mapped the trajectories and the later distributions of stars passing repetitively through the accretion disk, which is similar to the AGN environment. So the initial trajectory of the star has a non-zero inclination and is elliptic, is of an elliptic character. And due to the repetitive intersections and interactions with the accretion disk, the star will be dragged down to the orbital plane of the accretion disk itself. So this is in some sense the starting point of our model to come to the point where the star is in the orbital plane of the accretion disk. And after a short period of time, the trajectory will become circularized. And well, the star will eventually spiral down to the supermassive black hole. So, assuming the accretion disk around the supermassive black hole to be thin, I mean Shakura-Sunyaev thin, there might be two scenarios that that happen once the star reaches the orbital plane of the accretion disk. So if the sphere, some sort of sphere of influence of the star is bigger than the accretion disk scale height, there is a gap created, which is filled by the star itself. But in case the sphere of the influence of the star is less, so smaller than the accretion disk scale height, there's no gap formation in that particular case, and instead there are density waves created, which then propagate through the accretion disk that's present prior to this process. So in this picture, in our toy model, we ended up with a star having the ratio that favors the gap formation, and it will eventually move closer and closer to the supermassive black hole, slowly circling down to the terminal distance called tidal radius. Yeah. So imagine an object, say star, passing around a supermassive black hole or a very compact object. So once the star gets to a certain distance, which is marked by the balance of its self-gravity and the gravitational interaction of the two-body system, so the star will be tidally disrupted or tidally shredded. So the forces due to which this happens are of tidal character, and that is why this distance is called tidal radius, and it is given. It was first noticed by Hills and Rees. Hills in 1975 and Rees in 1988, and is given by the mass of the supermassive object at the center and mass of the star and its radius. Yeah, so this kind of event is called tidal disruption event, and it's shortly marked as TDE. And this came from the article by Rees from 1988, shows scheme for such an event, together with something like energetic gas or balance. And it points out that usually like half of the mass of the passing star will be wrapped around the supermassive black hole and will eventually end up being part of the accretion disk, or will create the accretion disk itself, while the other half will fly away on hyperbolic orbit to the infinity with the speeds up to the 10 to the 4 kilometer per second. So our aim was to simulate spectral line profile radiation coming from an accretion disk with not only one gap, but with multiple gaps, in this case with 2 gaps. And to somehow map what is happening in this system, we suppose the whole system is immersed in high energetic medium in corona. So based on the comparison of the size of the corona to the size of the accretion disk, there are like 2 possible, or typically 2 initial intensities of the reflected radiation. Once 1 over r squared. This is for the case when the corona is about the same size as the accretion disk. And the other one is 1 over r cubed, and this is for the case when the corona is bigger than the accretion disk. So one of the intensities on 1 over r squared can be seen on the top left panel, and 1 over r cubed on the top right panel. And this is the model A, which is representing the vertical slice of the accretion disk having 2 gaps, so the gappy ring. And we can observe that the presence of the 2 gaps will project onto on the multiplied number of spectral line peaks in both cases. To be precise, the spectral line peaks are tripled. And we also see that the flux is lower than in the unperturbed case. Well, the unperturbed case is the spectral line coming from the accretion disk without gaps. So if we let the gaps grow bigger, we might be converging to the scenario when we are having a ring-like structure. So not the accretion disk with gaps anymore, but instead of that, rings. And in this case, it's also visible that we have the tripled amount of the spectral line peaks. But what is more observable is the flux decrease, which is somehow understandable as the reflection area is diminished due to the size of the gaps, or due to the smaller rings. So that is why the amount of radiation we observe is much less. So these plots show the comparison of model A and model B, which simply point out the flux decrease difference in both models, and the ratios. The ratio panel at the bottom of each model shows the ratio of the perturbed spectral line to the unperturbed one, which makes even more visible the presence and position of the additional spectral line peaks that will come to existence due to the existence of the gaps themselves. So this is for the initial intensity as 1 over r squared, and this is something for the 1 over r cubed. In case of the model B, we can also see that it's even better mapped out, as it's like a bit more stretched. So recent observations show that a possible tidal disruption event might have been present in an AGN, which caused a drastic X-ray property change of the radiation, which was first discussed by Ritchie et al. In 2020. And this is the picture from their article, where in the first panel we see the pre-stage prior to the tidal disruption with accretion disk, supermassive black hole at the center, and the X-ray corona present, well, slightly above the accretion disk. In the next panel, we might observe that the interaction of the debris due to the tidal disruption at the tidal radius causes the accretion rate to be increased, which then turns out that the inner part of the accretion disk is depleted from the tidal radius downward. So this is something like gap creation in the inner part of the accretion disk. And in the last panel, it takes about 300 days to renew the inner part of the accretion disk with the infalling matter, and to like reinstate back the X-ray corona and to make it observable again. So the mechanism of the gap creation in this case is is slightly different from ours, but it makes it clear that events like these of this nature can be observable and might have some astrophysical realization. So in summary, in our case, we for the start have that the n number of gaps in the accretion disk will eventually result in 2n plus 2 peaks in the spectral line profile that we observe. I mean, of the reflected radiation of the accretion disk. The model A versus the model B, so it's like the gappy disk versus the ring-like structure around the supermassive black hole show that lower flux in the later and also the clearly distinguishable peaks. And it also points out that the given appropriate physical interpretation of the gap creation might lead to some astrophysical results, hence the changing look events observed. Yeah, so that's about it. Thank you. Can you hear me?
Yes, where is our chairman? Martin Kolosh is not here.
Okay. I just thought I was speaking to no one. I was afraid
so
it froze.
thanks for very nice talk. And if there are any questions, now is the time to ask. Okay, John Miller would like to ask something.
Okay, can you hear me?
Yes.
Yeah.
I'm succeeding better now and getting heard when I'm trying to ask a question. At the beginning of the talk, you said that the star on the inclined orbit is creating a gap in the accretion disk if the sphere of influence of the star is bigger than the disk height.
Yep.
I wonder if you could say a bit more about that. About what is happening in the sphere of influence and how big is it in comparison with the star itself?
Yeah, it actually depends on the physics, on the approach that you choose. So one might be the Hill radius, something like gravitational sphere of the star in the face of the perturbations coming from the supermassive black hole. So that would cause to be the gap to be slightly bigger than the star itself. But if we assume the magnetic field of the star and stellar wind, the sphere of influence might be much bigger. So this is probably something that we will aim for. We haven't really discussed the physics behind the gap creation yet. So this is something like a set of description, spectral line profiles, and the interpretation of the gap and the further slides for the spectral line profiles will come after.
Okay, thank you.
Thank you for the question.
Are there any more questions? Okay. So if there are none, so thanks, Marcel, Štolc again.
Thank you.
And